Good evening, everybody. My name is Spiros Patsourakos, and on behalf of the Governing Council of the Hellenic Astronomical Society, I would like to welcome you to the sixth monthly colloquium of Hel.A.S. Today's speaker is Dr. Evanthia Hatziminaoglou from European South Observatory at Garching in Germany. We are very happy to have together Evanthia. So a few words about Evanthia. Evanthia graduated from the physics department of the Aristotle University of Thessaloniki in '96 and obtained her PhD in France in Observatoire Midi-Pyrénées. The topic of her PhD thesis was on the formation and evolution of quasars and the corresponding cosmological constraints. Since she obtained her PhD, she initially shortly worked in Germany, then moved till 2003 at TISO, then moved southward towards more pleasant climates at EASE, where she spent almost 3.5 years as a Herschel-Spire postdoc. And since 2006, she joined at various positions the European Southern Observatory. Since 2012, Evanthia joined the Alma consortium at ESA, and she is currently the coordinator of the European ARC nodes network. The expertise of Evanthia is on the study of the statistical and physical properties of active galactic nuclei. She has worked on various aspects of quasar formation and evolution, and over the time, she gradually shifted her interest and her studies towards longer wavelengths, studying the physics of Tori, star-based AGN connections, and their implications to the unified scheme, mainly in the infrared in sub-millimeter wavelengths. Today's seminar that we are all looking forward to is on the largest radio astronomical facility in the world, Alma. So given her key position in the Alma project, Evanthia will give us all the important information and highlights about the technical characteristics of Alma, its scientific capabilities, a set of scientific highlights, of course, the path forward, and how one may get involved in doing his or her research with Alpha. Without any further notice, I'm giving the floor to Evanthia.
Well, thank you very much, Spiro. Thank you for this invitation. I'm very happy to be able to share this, present this talk to you, actually. I want to say up front, this is not a purely scientific talk. This is more of an informative talk, and I hope that by the end of it, those aspects of Alma that have been hidden from you until now will be also revealed. So let me start from the beginning, and the beginning is in fact the history of Alma, and my slides will not change. There you go. So already in the 80s and 90s, the European, Japanese, and American communities were independently started to thinking of the next generation millimeter interferometry facility with the characteristics of Alma. It so happened, however, that both the technology, the complications with the technology, and the prohibitive costs made it so that individually this was not possible to be achieved. So the three regions joined forces, and in 1995 they started running tests at the Atacama Desert. So the ESO, the European Southern Observatory, the National Radio Astronomy Observatory, NRAO in North America, and the National Astronomical Observatory of Japan, NAOJ. In 1999, these three observatories signed a cooperation agreement with the government of Chile to install Alma in Chile. And here to the right, you see Catherine Cesarski, the then DG with a beige top, signing the agreement with the Chilean government. 6 years later, the first stone was cast in the Altiplano of Chajnantor. In late 2008, the first 12-meter antenna that was built by the Mitsubishi Electric Corporation for NAOJ was handed over to the observatory. And October 2011 marks the start of cycle 0 early science observations. At the time we were observing with 16 antennas. And here to the right is an image of the antenna galaxies, which I believe is one of the very first images ever taken with Alma. Alma was inaugurated in 2013, in March 2013, in fact. And also at the same year, the last antenna was a European antenna that you can see here on the photo was delivered, and this also marked the end of the construction. Now, Alma is a truly distributed project in all senses of the word. The partners are Europe, North America, and East Asia. Chile is is a hosting country, and Chilean astronomers, as a result, have access to 10% of the observing time with Alma. Overall, and through the partners, more than 20 countries are involved in this project, and the total construction cost was about $1.6 billion US dollars. Now, the Alma partners are ESO, NAOJ, and NRAO. At ESO means the 16 member states. NRAO is North America, which represents North America with US and Canada, and in East Asia, the parties are Japan, South Korea, and Taiwan. And they are sharing construction costs and operation costs. Chile is, of course, contributing with the most amazing observation site ever. The Alma regional centers, the ARCs that are sitting in each of the regions, are the actual interface with the community. They are responsible for the user support. They are members of the integrated teams. The integrated teams are integrated science teams, computing and engineering. They provide subsystem scientists for several of the subsystems, astronomers on duties, expertise at all levels. And the joint Alma Observatory in Chile is responsible for day-to-day operations, astronomer duty shifts, and array operators. They are leading the integrated teams and many other things. This is just to give you an idea of the distribution of the tasks, and also of the fact that the tasks are very well distributed among the various parties. Now, even in Chile, the project is not in one place, but in 3 different places. So the offices are in Santiago, at the JO, the Joint Alma Observatory. The offices are actually in the same premises as ESO, it's just across a small street. The observations are run by the operations support facility at 3,000 meters, which is around here. It's very close to San Pedro de Atacama, about 40 minutes drive. And the antennas are up here. I'm saying up here and up there. I'm hoping that you can see my cursor. The antennas are at 5,000 meters at the Altiplano of Chajnantor at the border with Bolivia. And then this is a map that gives you a better idea of the orientation and the situation of the things. So the observation support facilities is here, the one that is down at 3,000 meters. Here is the, where the red buildings are, is the maintenance, the actual offices where we run the observations from. The green stuff is the residencia where we sleep, where we eat, and various other things. The gray buildings are the maintenance buildings. And then if you go up to the array operation side of the 5,000 meters, you can see Apex on one side of the road. Apex is the prototype Alma antenna, which is now operating as a single dish individually. And then to the other side of the road, you can see the location of the antennas in orange, and then in red, the technical building that is hosting the correlator. I will come back to that later. And of course, also our users are distributed all over the world. This is a map that shows where the proposals for cycle 5 were submitted from. So you can see it's from really all over the world, and we even have proposals that were submitted from Greece. Now let's look at Alma as an instrument. So Alma operates in the sub-millimeter range down here, meaning between 30 and 950 gigahertz, or in terms of wavelengths from 10 to 0.3 millimeters. And this wavelength or frequency domain is divided in 10 bands. Bands 3 to 10 are already working since quite a few years now. Band 1 is being commissioned and band 2 is still being developed. Now regarding the Alma antennas, Alma is composed of 66 antennas. 54 have a diameter of 12 meters and 12 antennas have a diameter of 7 meters. And they have been developed in all 3 regions. So here to the top, you can see to the left is the American 12-meter antennas, to the middle is the ESO 12-meter antennas, and to the right is a 7-meter Japanese antennas. So they four 12-meter antennas plus the 12 7-meter antennas altogether are also form the ACA, the Atomic Compact Array or Morita Array. And you can see it at the bottom. These are the antennas that are clustered very close to each other. So these 12 antennas, as well as the 4 single dish antennas, are not moving. You will always find them in the same location. But most of the other antennas can be moved around and placed on these white triangles, the pads, depending on the configuration we want to achieve. And in fact, the pad that is the furthest away is lying about, this direction about 16 kilometers away. So in fact, the longest baseline that Alma can achieve is 16 kilometers. Now each antenna weighs about 100 tons. And we have to move many of them regularly when we change configurations. And of course, you realize that we can't just go there, 3 of us, and lift them and put them to the next pad. So for this, there have been specially designed transporters that look like that. These are amazing machines. These were an ESO deliverable. They are 20 meters long, 10 meters wide, 6 meters high. They run on 28 wheels each. And without cargo, they weighed 130 tons. They're really quite something. They are called Otto and Lore. Of course, they have German names since they were constructed here. And here I will put a movie. I hope you can see how the antenna is going on the back of one of the 2 transporters. At the back here, you can see the operations facility center in white. I hope you had the time to see it. And other than the spectacular nature of the transporters themselves, it's actually a fact that you can also operate them with this remote control you can see here to the bottom right. Now the signal from all 66 antennas is collected and processed by a huge and very powerful computer, the so-called correlator, which is hosted as you remember, at the technical building at the high side of 5,000 meters. So this is a magnificent machine. It has 134 million processors, and they are capable to conduct 17 quintillion operations per second. In fact, this is 2 different correlators for the 12-meter and the ACA array. Now, in terms of observations with Alma, where the Alma time is divided among the 3 regions, Chile has 10%, and then the time among ESO, North America, and East Asia is divided proportional to their respective contribution to the project. 5% of the total available time, however, is available to astronomers that do not belong to any of these regions, which also means, of course, to Greek astronomers. As mentioned, the observations are run from the operations support facility located at 3,000 meters, more or less, well, 2,100 to be precise. And this is a part of the building with the offices, and the control room is there. And these are visitors here that we see more and more often. They have become quite aggressive lately. And this solmophore, as this is called, is something that tells you how much sunscreen you have to wear. In fact, when it's blue, like it is on the picture, it's best that you're not outside because the radiation is too strong. Now, Alma does not operate in visitor mode. All the observations are taken by trained Alma staff from the JEO and from the 3 arcs. And the control room looks a bit like that. To the right, you have a telescope operator that is monitoring the health and status of the antennas. And the other 3 monitors with the small monitors to the left are for the astronomers on duty. Observations at 12-meter and 7-meter and single dish are run in parallel. So these are 3 separate sets of observations that are running in parallel. And at any time, usually there are two array operators and two astronomers on duty present there, or at least this was the case in the pre-COVID times. Now I don't know how this is going to look like next time we go there. Well, as you know, Alma stopped operations in March 19, in fact, quite suddenly due to the pandemic. And so this is almost, well, in fact, next week it will be quite exactly 1 year since this happened. And now we're trying to recover and go back to science operations. The array recovery started in December, and the first antennas have already been handed over to science. The antenna recovery continues, and we hope that at some point soon we will be able to go back on sky. The cycle late call for proposals is anticipated to be issued next week, in fact. But of course, everything depends on the evolution of the pandemic in Chile and worldwide. The picture here is from taken by a drone, and it's you can see all the antennas parked during the shutdown. And they are also powered off. They're not powered at this moment. Now, if all goes well, the call will go out next week. The proposal deadline will be the 21st of April. Sorry, 17th of April, 2021. Yes. So for the first time, we're gonna give. Okay, am I mixing up here? Yes, it will be the 21st of April, sorry. We're giving 5 weeks for the first time to allow PIs to have a bit more time to prepare their proposals. And there are some new things that are offered in cycle 8 2021. I list here a few: solar observations in band 5, mosaicing of continuum linear polarization in bands 3 to 7 with a 12-meter array, 7-meter standalone high frequency, etc. You can go and have a look at the call when it is out, and this information is also already available at the pre-announcement. What's also new and of interest to all of us is that this time there will be distributed peer review for proposals requesting up to 25 hours in the main array, the 12-meter array. We will be doing double anonymous this time, so not only the PIs will not know who is reviewing their proposals, but also the proposals will not know who they are reviewing. Each proposal will go to roughly 10 reviewers like that. And another novelty is that there will be no phase 2 for PIs. So this means that at the time of submission, it's good to double check and triple check that every information we have inserted in our science goals is actually correct. We also anticipate that there will be an ACA supplemental call in September 2021, and with proposal deadline in the 6th of October. And again, everything really depends on the evolution of the pandemic. So all these are just indicative for now. Now, a couple of words on Alma user support, and in particular about the European Arc Network. The European Arc Network consists of the central arc at ISO, here marked in red, and 7 nodes in Onsala, Manchester, Leiden, Bonn, Cologne, Ondřejov in the Czech Republic, Grenoble, Iram, in fact, that is covering France, Spain, and the Max Plancks in Germany, and Bologna. For a number of years, we also had as part of the network, the Center of Expertise in Lisbon. This is no longer part of our network now. And the user support services offered by the network are first and foremost personalized user support in proposal preparation, data reduction, and archival research, help with phase 2. So every single approved Alma project will get a contact scientist, which is an Alma expert that will be following the project along with a PI from the moment of acceptance all the way to publication, basically. A lot of scientific community developments. There's a lot of workshops, schools, and educational initiatives organized throughout the network. And also there's a lot of quality assurance level 2. Basically, all the data that go into the archive are being QA2'd by experts at ISO and in the nodes. Something quite important here is that the European Arc Network is providing support also to users that do not have a local node, and actually also to users that have affiliations in countries that are not ISO member states. So even people from Greece, for example, can request to go for a face-to-face or virtual nowadays user support in any of the nodes. I also want to mention that as part of RadioNet, we had a dedicated work package that would allow us to finance the trips to the nodes. Now RadioNet is over, but the new joint RadioNet Opticon pilot program also has a dedicated work package that will be financing visits to the nodes. So when you get your Alma approved proposal and you need help, don't hesitate to contact the nodes you want to visit. So now I'm switching to a kind of a more scientific content part of the talk, and to discuss a bit the high-level science goals based on which Alma has been built and some science results. So the first, or the high-level, the three high-level science goals based on which Alma was developed was the detection of spectral line emission in a normal galaxy, a Milky Way type of galaxy at a redshift of 3 in less than 24 hours of observations, the imaging of gas kinematics in solar mass protoplanetary disks at a distance of 150 parsec, and imaging at an angular resolution of 0.1 arcsecond. So these were the requirements that drove the technical specifications of Alma, and these science goals could not and still cannot be achieved by any other instrument. So let's see how these requirements have been achieved. But before going there, I want to share with you some information about the Alma publication. So I extracted these plots this morning from the database. To date, there are 2,255 papers that are based on Alma data, be it proprietary or archival. And the color coding corresponds to the various scientific categories. You can see to the right that ISM star formation and active galaxies make up for about half of the publications, 70% if you add the disks and planet formation, and 85% including galaxy evolution. So the 2021, of course, is a dip because we're just in March. We experienced a small dip in a number of publications in 2020, and this is most likely due to the pandemic situation. But otherwise, the number of Alma-based publications is increasing every year, and this compares quite well with other big facilities, as you can see here. So Alma is in the thick blue line, and it follows very closely the publication evolution of the VLT, the HST, the XMM. So this is number of publications after number of years since the beginning of operations here. And what do Alma PIs observe? Well, emission lines, gas, CO, disks, and dust, mostly, as you will see now. So I will start with some highlights from our solar system. The first one is not so recent. It's actually one of the things that were observed as part of the long baseline campaign back in 2014. This is Juno, the asteroid. It's at a distance of 2 to 3 astronomical units. It's in fact one of my favorite because, of course, what you see is not the sunlight reflected on the surface. This is the actual light emitted at a temperature of minus 110 degrees Celsius, more or less. And you can see that the brightness is not uniform, but you can actually see these variations to the surface. And experts tell me that this tells them a lot of things about the regolith on the asteroid. Another nice result, I must say I chose these results just because I like them. There's no logic behind. I just want to showcase some of the things that, the amazing things that Alma has done. Another set of relatively recent observations is that of Europa, the satellite. This is a band 6 observations with a typical linear resolution of 200 kilometers. And this is actually the first spatially resolved thermal data set with complete coverage of the surface. And it's interesting because they used these measurements, this data, to revisit some models that were based on bolometric albedo measurements done by Voyager. So we had to wait several decades before we were able to revisit these models. Alma can also observe the sun. This is a band 6 image of the sun. This is actually the solar chromosphere that we see here. And this is also quite interesting because in one go, on the first, on one hand, the intensity gives you a distribution of the temperature of the chromosphere, and the polarization will also tell you simultaneously about the magnetic field. This is a zoom in one of the sunspots. And this is a screenshot I took. I happened to be at the OSF in one of the solar campaigns in 2018. And I took a screenshot of the monitor that was looking at the antennas. Remember, the antennas are far away. And I found it so cute that all the antennas would look like little soldiers towards the sun. It was just great. Another quite beautiful result, quite recent as well, is observations of the misaligned dust rings around the GW Orionis young triple star. So what you see here is band 6 dust continuum emission. This system is quite peculiar. So there are two stars very close to each other at the distance of one astronomical unit. And then there's a third star that is orbiting the double system. And then these three rings, they are at distances between 45 and 340 AU, and the two outer ones are obviously misaligned with the central one. Now, the reason of the misalignment is either the triple system itself, or perhaps the presence of a planet. This is not known yet, but we know from other observations, like the famous HL-Tau, for example, that this gaps, the rings in the disk, might be caused by planets that are being formed, and they are wiping the dust as they go around the star. But in this case, if there is a planet, a giant planet between the outer two rings, its distance, its average distance from the stars will be of about 220, 230 AU. This is a gigantic solar system. In comparison, Neptune is just like 30 AU away from the sun. Another nice thing I know nothing about, but I found it really interesting, is the detection of aluminum oxide around a candidate young stellar object. So this is in the Orion region, like all the other interesting stuff in our galaxy. These are, on the top is band 8 and the bottom is band 9 observations. The color one is the aluminum oxide line and the contours are continuum. Now, this object is known because it has a very strong outflow. And the interesting part here is that the aluminum oxide emission is concentrated at the base of this outflow. Now, why this is important? Well, aluminum oxide is actually a key element in the formation of small rocks, old rocks in our solar system. And this observations, they give us a chance to study the initial formation processes of meteorites and planets. Now, the fact that the emission of aluminum oxide is concentrated at the bottom of the, close to the start of the outflow, it means that where the temperature is higher, it means that further out, when the temperature drops, this thing may have already condensed into these dust clots. Now, moving quite far away, this is a almost perfect Einstein ring. This is a galaxy at a redshift of 4.2. Originally was observed with the South Pole telescope. And in fact, at this redshift, one expects that the random motions, in fact, dominate the dynamics of the galaxy. But from the reconstructed model, we found that in fact, the rotational models are the ones that dominate, and by a factor of almost 10 with respect to the random motions. So it's more like a Milky Way type of behavior, but at a redshift of 4 point plus. So no talk is complete without a quasar. So I had to put in a quasar. And this is not just any quasar. This is the highest redshift quasar known to date. It has been observed with Alma. This is to the left, you see the continuum map. To the middle is C2 map at 158 micron. And this is a quasar at redshift 7.642. And based on the multi-wavelength observations, the derived black hole mass is 10 to the 9 solar masses. And this definitely poses challenges to the theoretical models of star supermassive black hole growth, because this is really only about 670 mega years after the Big Bang. Another nice thing, it's already a couple of years old, is the detection of oxygen 3 line, the 88 micron line from a galaxy at a redshift of 9.11. Now, the detection of this line at that redshift means that there is ongoing star formation at that moment. However, the multi-wavelength SED also has a much older component, which indicates stellar component, which indicates that the star formation in this object has started sometime at a redshift of around 15, like 250 mega years after the Big Bang. And of course, I could not leave this outside. I'm sure you've all seen the image of the shadow of the black hole in M87. So this is band 6 observations, and of course they made the news worldwide. What is perhaps a bit less known is that it's really thanks to Alma that we got this fantastic image here. Here to the right, you see the image without the contribution of Alma and Apex. And in fact, without Alma, I think we wouldn't have been able to measure the properties that were measured based on the model behind this image, like the black hole mass and the spin. Alma has also invested quite some time in large programs. We have started offering large programs in cycle 4, and it's been so now 4 cycles that large programs are running. I have selected a couple just to showcase what Alma can do, and most of the ones I selected have their PIs in Europe. So starting from the most distant universe, the Alma large program to investigate C2 at early times, or otherwise Alpine. The PI is the late Olivier Lefebvre from Marseille. So these are band 7 observations of a sample of 122 star-forming galaxies at redshifts between 4.4 and 5.9. And what they have found already, all these are ongoing projects, of course, and there is still to be a lot to be discovered, but first findings of this project is that a significant fraction of the star formation at this epoch is already hidden behind dust, and that a large fraction of these galaxies have distributed morphologies and ubiquitous gas outflows. Coming slightly closer is the aspects. This is a cycle 4 large program. In fact, the PI is Fabian Waltzer from Heidelberg. This is a blind survey scan for CO and continuum in the Hubble ultra deep field. And they have already found a number of interesting things, which I list here, but for the sake of time, I think I will just go to my next slide, which is FANGS. Again, a large project. This is from cycle 5. This is led from Eva Shinra, which is also based at the Max Planck in Heidelberg. This is band 6 observations of 74 nearby galaxies, and they wanted to resolve Orion Nebula-like structures in these galaxies, and they managed to do so, more than 100,000 of those. They are targeting CO 2-to-1 emission at a common resolution of 90 parsec, and they try to understand the interplay between small-scale physics and galactic structure and galaxy evolution. And of course, what they found is a large variety of things that vary both with galactostatic radius and as a function of dynamic environment, and many more. Now, this one is not led by European PI, but I chose it because it produced spectacular images. This is the second cycle 4 large program, DSHARP. The PI is Sean Andrews. They observed 20 protoplanetary disks at very high resolution, 5 AU resolution, so 35 milliarc seconds. And they found, in fact, that they all have substructures, and that the most common substructure is gaps and rings, like the ones we've seen before. Spiral substructures are less common, and so are multiple systems. The last large program I want to mention is Atomium, is a cycle 6 program led by Lynn Dessine in Belgium. And this is band 6 CO observations of 12 AGB stars. They were selected to have a variety of properties. And the most important result so far, again, work is ongoing, is that the substellar binary activity is what is actually dominating the shaping mechanisms of this, the AGB stellar winds and their successors, the planetary nebulae. So now I have convinced you that Alma has achieved manifold the original 3 high-level science goals, but we're already looking ahead, we're thinking ahead, and the Alma 2030 roadmap was already put together a couple of years ago with new fundamental science drivers that are again driving the future developments. So these new science drivers are tracing the cosmic evolution of key elements from the first galaxies all the way to the peak of the star formation at around 2 to 4, and to be able to do that at a rate of 1 to 2 galaxies per hour, trace the evolution from simple to complex organic molecules in solar system scale systems, so in resolutions of 10 to 100 AU, and doing so by observing 2 to 4 protostars per day. And finally, imaging protoplanetary disks in nearby star formation regions to resolve the Earth forming zone. So 1 AU, we've done 5, we want to go down to 1 now. So achieving any of these science drivers is currently impossible with the capabilities of Alma. So, and these new goals are what are the goals that are driving the upgrades proposed in the Alma 2030 roadmap. And these upgrades touch upon many aspects of Alma. First of all, the receivers, digitizers, and correlators, the archive. And of course, there are some identified midterm opportunities that are related to future developments. So first, going for the first part, the first important thing is to upgrade the digitizers to make sure that they can record wider, larger bandwidths. Without that, we cannot talk about, upgrade of the receivers or the correlator or whatever. So the first step is the receivers, and this is really the first step towards realizing the 2030 roadmap. Once this is done, then we can think of upgrading the receivers to deliver larger IF bandwidth. And this means that the imaging speed will increase. And so will the efficacy of spectral scans. And if the receivers are upgraded in the way that is foreseen, this will mean an increased efficacy by orders of several, in fact. And finally, the new correlator will have to be able to process this larger bandwidth and higher spectral resolutions. Following these developments, also the Alma Archive will have to adapt itself. It will have to be able to not only store larger data sets, but also provide a way for users to access them in better and more easy ways. We'd also have to allow for a more efficient exploitation of the wealth of data that is already in there and that will be accumulated in the decades to come. And in particular, attention will have to be paid towards data mining of the Alma Spectra products, because even now, with the moderately large data sets, a lot of the information that is hiding inside the data, the Alma data set, is not being used to its full potential. Finally, there are some midterm opportunities that have been identified as part of the 2030 roadmap. First of all is, of course, extended baseline. This will allow for higher resolution. They are looking into focal plane arrays that will allow for an increase of wide field mapping speed. Additional to have emitter antennas, of course, is a no-brainer. It will increase the sensitivity and or decrease the integration time. And finally, it has been pointed out that a large single dish capable of observing at sub-millimeter wavelengths will, of course, increase the survey speed manifold. Now, this last one is recommended, but it's completely outside the scope of ALMA, and this is very clearly stressed in the ALMA roadmap. Nevertheless, there are initiatives that are looking into this last possibility, and my last two slides will be dedicated to that. It's actually an advertisement about the Atacama Large Aperture Sub-Millimeter Telescope, or otherwise AT-LAST. So currently, there is no large dish in the southern sky that can observe beyond about 400 gigahertz, and that has a diameter beyond 12 meters and a field of view above 1 degree, more or less. And this is what we are after with this initiative. With AT-LAST, we want to have about 50-meter antenna that will have about, well, actually hundreds of times lower confusion noise than a 6-meter sub-millimeter survey telescope, such as the CCAT Prime currently, and will have no confusion limit at the 350 micron. So this is band 7 for ALMA. And this is the AT-LAST design study that was approved for support by Horizons 2020 for a 50-meter dish that will deliver a construction-ready design for AT-LAST. So this is a program that we submitted about a year and a half ago to the EU. This is not an ESO project. ESO has nothing to do with it. It just so happens that 3 of the 6 work packages are led by ESO people, ESO astronomers on their science time, not on their duty time, taking advantage of their expertise. So the PI and leader of the project management work package is Claudia Ciccone from the University of Oslo. The telescope design is led by Tony Mroszkowski from ESO. The site selection is led by Carlos de Broek from ESO. The telescope operations I'm leading, again, ESO. Environmental sustainability is led by Sabrina Santori at the University of Oslo, and the science case is by Pamela Claassen in the UK. We have obtained funding for 3 years, and the kickoff is next week, in fact. And this is really an open collaboration. We want to engage the community as much as possible. So if you are interested in contributing in any way, including the science cases, please contact any of us. And I think with this, yes, thank you very much for your attention. I think I went a bit too fast, but well, there's more time for discussion. Thanks.
Thank you very much, Evanthia, for the very nice and comprehensive talk. So now we have time for questions, comments, etc. So please, whoever wants to speak first.
Well, it was either too clear or too boring.
Hello, can you hear me?
Yes.
Yes, I want to ask, can somebody use ALMA for detecting not so much exoplanets, but exoasteroids or things like that, looking a little bit like dust or bigger particles?
So what distances are we talking about? You're not talking about our solar system, you're talking about other solar systems, right?
Other solar systems, yes.
Yeah, again, I mean, this is resolution-wise is impossible. So what you see now, the resolution of these disks that we see, the dust around the protoplanetary disks are of the order of some AU. So this is really well beyond anything that ALMA can do.
Okay, thank you.
Hi, Evanthia. Daniel here.
Hey, hola.
I wanted to, hola, ¿qué tal? I wanted to ask you, from all the upgrades that you described at the very end in terms of increasing the number of antennas, the longer baselines, improvement of the correlator, larger bandwidth, I assume that not all of them will be funded, or only a fraction, and if so, which do you think have the largest chances of being funded?
Well, I think receivers, digitizers, correlator, and archive are a must. It's we have to go that way, and there are also various, well, a few studies underway on the digitizers, on the correlator right now. So these things, I believe, will have to be done. Now there is also a study on extending the baselines. A single dish is out of scope, as I said, this is not going to happen, but most of the other things, well, most of the digitizer, correlator, archive, and receivers will be done, yes, most likely.
Hi, this is Antonis Georgakakis. My question is on the roadmap 2030, and whether there is something specific in that plan regarding coordination with large ESA missions that will occur on at that time scale. And I'm thinking about Athena, maybe LISA, ELISA, or even Euclid. I mean, Euclid is a little bit earlier, but yeah.
Well, I think this is not part of the roadmap, because the roadmap really focuses on technological development for Alma. But I'm sure there are various discussions in the community and at various levels on how to best explore such future synergies when the time comes.
Okay, thanks.
I see Costas has his hand raised.
Hi, yes, thanks for the nice talk. So I wanted to ask for us in Greece, it's probably very important and valuable to have access to the archival data. So could you elaborate how this process works? Does somebody need scientific support from the experts, or are the data products high enough that somebody can just look at them and use them directly?
Okay, so there are various things there. So the Alma data, like other facilities, they undergo a 1-year proprietary time, after which they are open to everybody. So you can go to the Alma Archive and download them. All the data that are in the Alma Archive have undergone a quality assurance process. So the QA2 I was talking about before. But first they have been calibrated. So they're calibrated and imaged. So the calibration is science ready. You can really take it as it is, or request the calibrated measurement sets to be delivered to you directly, because from the archive you will have to recreate them yourself. But we offer the possibility to do it in the ARCs and give it to the users. But then the image data that are in the archive are good enough for you to get an idea of the capabilities of this data set, of the content of the data set. But really, if you want to extract the most out of a data set, you will have to re-image yourself, because there is a lot of stuff that a lot of decisions that go into re-imaging, into imaging your data, that really are very specific to your science goal. So it is recommended that you ask for support from any of the ARC nodes in Europe, in fact, and they will be more than happy to do that.
And this does not go through any competitive process, so there is no selection process. Anybody can just apply for help.
Yeah. Once the data are publicly available, you can just send a help desk ticket. So all you need to do is to have an Alma account. You send the help desk ticket, and then from there things take their course. You will be assigned. You can request a specific node for support, or even a specific person if it is that you're in contact with somebody, and then you will be given all the support that you need. There is really no triage in a sense. Whoever requests support will get it.
Thank you.
Mm-hmm.
Other questions, comments? I got one. What is the average success rate of the Alma science proposals? And do you have any idea how it compares with other radio facilities around the globe?
Well, the oversubscription has stabilized at around 4.5 to 5, I think. This is a bit region dependent, so the pressure is higher in Europe than it is in North America and East Asia, but this gives you a bit an idea of how easy or difficult it is to get Alma data.
Okay, thanks. Any other question, comment?
Now a question, it's me again. In a few years, we are going to have a big telescope for visible and little bit of infrared and the ELT. We are going to have a James Webb telescope. Now you informed us that Alma is going to have going to grow, let's say it like this. So do you think that in about 10 years, we are going to be in a better, we are going to make a very big step to the multimedia astronomy, combining all the kind of observers, facilities?
Well, I think...
Okay, thank you.
Sorry, go ahead.
Yeah, about the multimedia astronomy and the big telescopes what we're going to have in...
Yeah. Okay, so maybe perhaps not in 10 years, because in 10 years, Alma will not have upgraded fully. It will be only, I think, starting to fully upgrade its capabilities. Also, I'm not quite sure what the status of the ELT will be in 10 years' time, but I think we are going to see some evolution indeed in our understanding of the universe in the coming 10, 20 years as all these big facilities are coming online, indeed. Ah, Nureddin.
Hi, Eva.
Hi.
In something like 20 plus years, we have not seen each other.
I can't hear you.
I know. I said it's so nice to see you after so long. I mean, it's been something like 23 years we have not met. Yes. So I have, and I'm really impressed with what you are doing, and it's really great. I have a question about the data policy and solar observation. So what is the data policy? Is it public right away, or there is a certain latency before it becomes public?
All PI, Alma PI data, they have a proprietary time of a year, apart from the programs that have been awarded the director's discretionary time, the DDT projects that have 6 months proprietary time. But otherwise, all the projects have 1 year proprietary time.
Okay. And for the other questions I have is, you showed the solar observation, and they look amazing. How much time do you have for solar observations? I know you have a lot of pressure. Everybody is trying to get observing time. How much do you have for the sun?
So at the beginning, the solar observations were run in a solar campaign mode. I think now this is no longer the case, but it's we don't have, I don't believe we have dedicated slots for solar observation. It just depends on the number of approved solar projects, basically.
Okay. I was asking because for every now and then we run big campaigns for Parca Solar Probe, and we solicit support from all over the world. We had 2 campaigns, and for a couple of them, we had 50 plus observatories supporting us. And if we get some time from Alma, that would be fantastic.
Mm-hmm. Yeah, all you need to do is to apply in the next call.
Okay, I'll do that. Thank you.
Thank you, Nur, and I second this for Solar Orbiter.
Magda?
Hi, hello for the very interesting talk. So I was wondering, I heard you saying that there are a lot of data that are not explored yet, and the full potential of the data that are available is not really used yet. So I was wondering what are the requirements, which software we need to develop, or what are the requirements, what we need to do to explore the data in their full potential.
Okay, so there are various things there. So the thing is that, you know, PIs have some science goal in mind where they propose for Alma data. So they propose, they get their data, they do the science they propose for, and then they often move to the next project. But Alma data are, you know, sometimes there are like, you know, for example, emission lines in there and nobody has looked for them because the original science goal was not centered on those emission lines, but something else. So it's not that we're lacking the software, it's that there is so much data by now that there is perhaps not enough manpower to plow through all the data and check all the possibilities.
I get it. Thank you.
May I? It's Calliope, that's here.
Sure. Hi, Calliope.
Yeah, so the question is a bit technical because we're considering, well, you know, considering for the future building some antenna in Greece. And we have been discussing the antennas of Alma. We're discussing building something, some facility in any case. The question is the brands, the antenna brands. I know of the AEM. I know that the ones that have carbon fiber layers, they tend to have a shorter lifespan. So if you were to advise us where to start with respect to antennas, the market and cost and whatever, and that would be great. I mean, we're trying to come up with a proposal for a national facility that could join other observatories in the future, because it's quite a fashionable that countries add like small antennas to big networks these days, and we could in principle do it. So we're wondering, you know, we're investigating right now.
Okay, well, this is definitely not an answer I can give you, and definitely not right now, but I can definitely give you the name of people that will give you very informed answers on this.
I'd appreciate that. And we will put you into the loop if you're interested as well.
Taking notes.
Yep, thanks a lot.
Other questions? Noor, do you want to comment furthermore, or you just forgot your hand?
Oh, no, I just forgot my hand.
Okay,
Sorry.
Okay. So it seems we have finally a very active and interesting Q&A session. So let's thank again very much Evanthia for... Lucero?
Sorry, no, I just want to thank for the talk. It was a very nice review, and also listen a bit of Greek at the beginning. I miss it a lot. So I just send my greetings from Mexico. Thank you.
Okay, hola. Okay. So thank you very much, Evanthia. Thank you very much, everybody. Take care and see you in 1 month.
All right, well, thanks very much, everybody.
Yes.
Bye-bye.
Bye.